thank you very much, and let me first...
Sorry, from the very end asked to use this. Okay.
Is it fine like this? Okay. So I'm very pleased to give this lecture here, and I thank Professor Lamazova for inviting me. It was very kind, and I'm really pleased to be here for 1 week and work together with her and with Raman Nesterov. And as Professor Lamazova already told, we have an ongoing cooperation, so there might be other occasions to meet. But today, actually, I won't deal with the current subject of our cooperation. I will talk about something which is a current subject of research in my small group in Milano-Bicocca. And by the way, no? Yes. Let me first acknowledge my colleagues who contributed to what I am going to present. I am going to talk about a kind of game, not really closely connected to what you might know as game theory in mathematics, even if there are some connections, but a game which has some similarity to the usual board games like chess and the like, with a very important difference that I will try to stress later, and which is implicit in the adjective asynchronous. But I think I can explain it more clearly in a while. So let me try to describe the general setting that I'm interested in dealing with. By the way, please feel free to interrupt me if something is not clear, if you have some questions or comments. So we assume that there is a player. Player is a generic term. You might call it an agent or any entity, which is interacting with an environment. Interaction can take several forms, but we will assume that we can describe what happens in this system by means of a set of events, something that happens, that occurs, and can be performed either by the player or by the environment, or sometimes by both together. So this is a very general framework. You can think of many real-life situations which can be described like this. We are interested in particular in cases in which the player has a goal, want to achieve a specific goal. For instance, he would like to be able to perform a specific action, or maybe he is willing to avoid that something bad for him or her will happen, or many other possible goals. We also assume that the player has a full knowledge of the structure of the system. He knows what can happen, but has only a partial knowledge of the current state of the system, cannot directly see anything that happens. So if the system evolves by performing actions, we assume that the player can directly observe only some of the actions and must try to understand from what he observes the rest that happened before or is going on now. So the events in the system are only partially observed by this player. The role of the environment can be the role of an opponent. We might think that the environment is against the player, and so we'll try to contrast the goal, the player in trying to achieve its goal, or maybe just indifferent. So the environment doesn't care about what the player is trying to do, but this means that the environment is not necessarily collaborative with the player. There is a last assumption that I make, which has a more technical nature. I assume that the environment must progress, meaning that if something can happen in the system, and this something is under the control of the environment, then something will sooner or later happen. The system cannot just be blocked by the environment. Now, in order to study from a formal mathematical point of view such a kind of system, we need a formal model, some way of precisely representing, even if in a simplified or abstract way, the system that we are interested in studying. And since the player and the environment can act concurrently, they can make actions at the same time, we need some formal models which is specifically designed for representing such kind of systems. And there are many of these formal models. I mentioned here a few, maybe you have already met some of them. Process algebras, actor systems, automata, Petri nets. From a more practical point of view, maybe you have already written some concurrent programs. That's the kind of system in which several instructions can be performed at the same time. So among the many formal models available, I will use Petri nets, and more specifically, a type of Petri nets which is called elementary net systems. Now, in general, a Petri net is an object which is made of two kind of basic elements: local states and transformations of states. So the idea is that we describe a system by specifying some conditions that can be observed in the various places of this distributed or concurrent system. And more specifically, in elementary net systems, these local states are just sort of Boolean variables that describe something that can be true or false at a given instant. For instance, I might describe this room, at least one part of this room, by specifying that this light is now off, that light is now on, and so on. So these are local states because I described just a small part of the system, and they are, at least in part, independent one another. So we have such a set of local states, which is represented by set P. But of course, I'm interested in describing how the system can evolve in time. So in my description, there are also actions or transitions or events. This is the set T, and each event or each transition is represented by specifying what are the preconditions for that event to occur and what are the effects in the case that the event occurs. Maybe Petri nets are more easily understood if we look at the graphical representation, which I will give in a while. This is still some formal definition. I think you should easily follow them, but anyway, in the representation of the system, for each transition, I specify what are the preconditions, and these will be some of the local states, and I specify what are the effects, and these will be other local states. So the event can occur, can happen, only if all its preconditions are now true, and the effect will be that the preconditions will become false and the post-conditions will become true. The effects or post-conditions will become true. Actually, in elementary net systems, we graphically represent the elements of a net like this. This is just a small part of a net. The squares represent the transitions, so what can happen. The circles represent places or local states or conditions. And with those small black marks, I show which of these local states are now true at a given instant. So now, for instance, the transition that you see on the left, in this case, is enabled, might occur, because all the preconditions, which are the places with an arrow going to the transition, are marked, so I consider them as true, and the effects are now false. So the transition might occur, and if it occurs, then the preconditions will become false, the postconditions will become true. The transition on the right, in that situation, is not enabled, cannot occur, because even if all the preconditions are true, there is one postcondition which is also true. So that transition, in some sense, cannot really produce its intended effects. That's the formal choice for elementary net systems. There are other kinds of Petri nets which maybe, do they know them already? Not yet. Okay, well, there are some other kinds, but for now we can focus on this. So this is an example of a whole elementary net system. Maybe I can spend 1 minute trying to describe what this can model. As you see, there are several local states named P1, P2, and so on, through P7, and some transitions, some events or actions, T1, T2, and so on, up to T7. As you see in this situation, in the situation depicted by this system, the local states P1 and P2 are true. For instance, they might say that this light is on and that light is on. And this allows events T1, T2, T3, and T4 to occur. They might occur because their preconditions are true and their postconditions are false. But as you see, for instance, T1 and T2 have one precondition in common, which is P1. Then the so-called firing rule, the rule of evolution of this kind of nets, says that only one of them will actually occur. There is a conflict because it's like they share a resource and only one of them can actually use the resource, at least in this situation. So if we want to play on this model, we can decide whether to fire, which is the technical term to mean that a transition occurs, to fire either T1 or T2. And this will have different effects. And on the other hand, and independently, we can choose whether to fire T3 or T4, with, again, different effects. And for instance, if we choose T1 and T3, so P1 will become false and P3 will become true, P2 will become false, P5 will become true. At that point, as you may see, event T5 will have all its preconditions, which are P3 and P5, true. And so that event, which in the depicted situation cannot occur, will be able to occur. So we can define this rule that specifies how the system can evolve in time. And if T5 occurs, then P7 will become true, and then T7 will be able to occur, and this will bring the system back to the initial state. So we can play this game and try to explore different possibilities, but since we are scientists, we want to systematically study all the possibilities. And there are many, several possible choices for systematically study all the possible, let's say, all the possible games on this board. Here there is an interesting situation. I have described a scenario in which T1 and T3 occur and then something else happens. But suppose that we choose T1 on the left and T4 on the right. Then after these events, P3 and P6 will be true as local states. And now, if we apply the firing rule that we saw before, we can check that there is no enabled transition. There is no transition which has all its preconditions true. So the system is dead. Nothing else can happen, which is something that unfortunately happens in real systems. For instance, a computer might freeze, maybe because there is no event enabled. And this is the final situation. So I was telling that we are interested in studying systematically all the possible evolutions of such a model. There are two main formal tools to study systematically the evolution of an elementary net system. One is called marking graph, the other is called unfolding, and I will focus on the second one because it is the one I want to use in describing a new game. So the unfolding of an elementary net system is another net made of local states and transitions. So it's an object which is similar to the starting one, but is potentially infinite. If you remember, in this net, if you follow the arrows, you see that there are some cycles at some point. This means that after a while, some condition which was true and became false can again become true. In the unfolding of that same net system, we just record what happened and we add new elements each time that something happens. So we will have occurrences of the elements of the net system. So for instance, here you see that element of this net, which I couldn't draw completely because it's infinite, have a label with a name, the name of an element of the original net, but I have added the number to distinguish this occurrence of P1 from the one which is down there, for instance, and so on. So here we can follow whatever can happen in the system. It's a sort of super log of what happens or what could happen in the system. And in this huge net, I can find, with a simple rule, possible actual histories of the system. Here I have depicted potentially all the possible alternatives, which depend on how we solve the conflicts that can be in the net. But the gray elements represent one possible history corresponding to some specific choices every time that I had a conflict in the elementary net system. And this is actually the first part of the history that I had described at the beginning, where the two choices were made in a clever way so that the behavior might continue. So the unfolding is this potentially infinite net, and we can define some interesting objects within such an infinite net. In particular, we are interested in what is a run. A run is what I have drawn here in gray. So one possible history, the record of one possible history in the system, with all choices solved. And so a run can be infinite. If the system is cyclic and can always return to the initial state, then a run might go on forever. A cut is a sort of a dual notion. A cut is a sort of vertical cut if we think that this represents the evolution in time of this system. If we draw a vertical line, we can cross elements which can coexist in a given instant in the system. And this is the notion of cut. And in particular, we will need B cut as a cut made only of places or local states. So now we come closer to the idea of game that models the situation I described in the beginning. So now we must think that we have drawn a net system, an elementary net system, representing the system made of a player and its environment. So the events in the net system, in the formal model, represent the actions that the player can perform or the environment can perform or both together can perform. And now we must specify what the player can directly observe in the system and what the player can actually control. So, with respect to the usual definition of elementary net system, we add the sets V and K. V is a subset of the transitions of the net and represents the set of observable transitions. So we assume that whenever some of these transition occurs, the player can immediately know that it has occurred, can observe directly this transition. And K, which is a subset of observable transitions, is the set of transitions that the player can directly control, which means that the player can decide whether to make one of these actions occur or not, or keep it, or postpone it, or even keep it blocked, if this is useful for his goal. If we have an elementary net system with these two sets specified, then we can still, of course, compute the unfolding, or at least ideally. And of course, we can mark in the unfolding which events are observable by the player and which are controlled by the player. So now we can define a game which is played on the unfolding. This game looks a bit like a game like chess, for instance, games which are played on a board, but with the important difference that I already noticed. Here, we cannot say that now it's the turn of player A, now it's the turn of player B. The two players can decide to move concurrently at the same moment, in some cases, of course. So a play, a single play, will be a run. There are some technical restrictions, but I don't think it's important to discuss them. So a play will be a run in which some choices have been taken. The player has decided to fire, to make happen some of the controllable transitions and maybe has kept blocked some others. And the environment has chosen its transitions. So with this definition, a play can be infinite. This is an important difference with respect to the usual games that we play, because usually we want to play a finite game and at some point be able to say, you win, you lose. But actually, even if a play is potentially infinite, we can still define in which cases the player wins and in which cases the environment wins. And there is a technical way to describe this winning condition. Of course, so far we have thought about a player which chooses randomly what to do. Usually, a player, a good player at least, will follow a strategy in achieving its goal. And we would like to be able to decide whether for a given situation, a given elementary net system and its unfolding, the player has a winning strategy or not. So we have to define what is a strategy, and to decide to define what is a strategy, we must take into account the fact that the player does not see everything that happens. So the player cannot base its choice on a full knowledge of what has happened so far. So formally, we define the notion of observable configuration, which is essentially the set of observable events that have actually happened so far in a given history, so in a given partial play. Here, for instance, the gray elements of the net and the green elements form a partial run, something that has happened so far. It is not yet a full play, because it might continue. And the green elements are the observable elements. So the green elements are what the user has actually observed. Maybe you can understand that by observing some elements, for instance, the green transition, which is slower, the player can deduce that something else must have happened before, even if this was not directly observable. Because for that transition to occur, it was necessary that something else happened before. So we can think to define a strategy as something that, on the basis of an observable configuration, decides what to do next, what controllable transition to use. And so this is the formal definition. If we call delta the set of all potential observable configurations, then a strategy will be a map, a function, from this set to the controllable events that represent what the player can decide to do autonomously. And once we have defined a strategy, we can define when a play is compliant with this strategy. A play in general is not bound to follow a specific strategy, but if we think that the player is using his strategy, then of course some play will be discarded because they become impossible. So a compliant play is a play in which all controllable events are the result of a decision by the player according to the strategy. So if I find a controllable event in such a play, then there should have been an observable configuration during the evolution of the system in which the strategy of the player decided to fire exactly that event. And then when the player has defined a strategy, we can define whether this strategy is winning or not. To decide if the strategy is winning, we must look, at least implicitly, to all compliant plays, all possible plays that follow the strategy, and see if each of them is won by the player. In this case, we will say that the strategy is winning. If there is just one play which is compliant to the strategy, but is won by the environment, then the strategy is not winning, because it does not guarantee that the player will certainly win. This is a sort of technical remark. As you have seen in elementary net systems, we can model situations of conflict, situations in which several transitions are possible, are enabled, but they share a resource and only one of them can use that resource. So in this case, we say that there is a conflict and only one of those transitions can actually happen. Well, a strategy in this game cannot rely on the ability to win a conflict with the environment. If in the model there is a conflict with the environment, then the player cannot hope to win that conflict. His strategy should allow for plays in which the environment wins the conflict and should be able to win even in those cases. So now we have a sort of general notion of game that can be played on unfoldings, on those kind of infinite Petri nets. Then we tried to apply this idea to a specific problem. Potentially, the game can be applied to many problems, and of course, according to the specific goal of the player, we will define different strategy. In order to check if this notion of game is meaningful, interesting, useful, we took a problem that had been defined independently of this idea of game and tried to apply this idea of game to that problem. The problem is called weak observable liveness and can be described like this. Suppose that we have an elementary net system like this one, and suppose that it is a controlled elementary net system, meaning that some transitions are controllable by a player, the other ones are controlled by the environment, so the player has no control on them. And in general, suppose that some transitions are observable by the player, some are not. Then we are interested in the following problem. We choose a transition and call it target transition. For instance, suppose that in this example we choose T7 as a target transition. And we declare that the goal of the player is to be able to fire this transition in the future. But this must be guaranteed. So the player must be able to control the evolution of the system so that he is sure that sooner or later this transition will fire. And since the system is cyclic and can always return to the initial state, we want to be able to make this transition occur infinitely often. In the meantime, of course, other transitions will fire necessarily, but we want to be able at any instant to reach a point in which T7 will occur. And in this example, I assume that the black transition, the black squares, correspond to the controllable transitions. So in this case, we assume that the player can control only T1 and T2. And if you recall the example at the beginning, then it should be clear that if the player wants to achieve its goal, so being able to fire T7, the player cannot choose at random either T1 or T2. But the choice should depend on which choice has been made by the environment in the other conflict. So it's crucial that the player can observe T3 and T4. If the player can observe T3 and T4, then, intuitively, at the beginning he must just wait until either T3 or T4 will fire. And since we assume that the environment cannot block the system, sooner or later the environment will be obliged to choose either T3 or T4, and at that point the strategy of the player can choose the right transition. And from then on, the behavior of the system is deterministic until we go back to the initial state, and there the player again will apply its strategy. So again, we have the assumption that the environment cannot be totally blocked. These are some formal definitions. In this case, we are not really talking about the game that I described. This idea of weak observable liveness was defined before. And so instead of the strategy, there is a notion of response function, which essentially models the behavior of the player. With an important difference, this response function is defined on the set V star. I don't know if you're familiar with this notation. This means all the possible sequences of symbols taken in the set V, which means the sequence of a sequence of observable transitions. So this response function, on the basis of what the player has observed so far, will decide to take some specific controllable transition. And then we can define when a full sequence of transitions that happened in the model is consistent with a response function. It's very similar to what we discussed about a compliant play with respect to a strategy. And then we will say that the transition T is weakly observably live if in every consistent sequence, which means in every behavior of the net which obeys to this response function, the target transition fires infinitely often. There is an infinite number of occurrences of that transition. Now, we can think of two special and interesting cases. One is actually the general case, the case of partial observability. So, as we told from the beginning, here we suppose that the player will observe only a part of the transitions. But in trying to apply the game on unfoldings to this problem, we started with the easy case. So we suppose that now the player can observe all the transitions. So can use the full information about what happened, and we'll try to define a strategy for this case. And then, in this example, we have already seen what is the best strategy. Wait for the environment to choose between T3 and T4, and then make the right choice between the controllable transitions. So, in order to apply our idea of game, we must compute the unfolding of the net, and then try to apply the game to this unfolding. So a play will be, again, as we defined before, a run, a possible history of the system in the unfolding. But we also suppose that someone, let's say someone who is looking at this play between player and environment, every now and then is able to take some snapshot of the system and see what is true at that point. But we assume that this cannot be made at any instant, but only at some points. So a play will be the run, describing what happened, and this sequence of snapshots of the system in some instance. And here, the hypothesis of total observability helps us because it simplifies a lot the search for a strategy. We can define a strategy not as a map from the from the observable configurations, but from these snapshots to the possible controllable events. So this is the formal definition of a strategy. So it's a function from the set of these snapshots, this representation of the actual current state of the system to the set of controllable events. And there are some technical restrictions, but they are not very important now. What is important is that now we can take our system, an elementary net system with a set of controllable transitions. We assume that everything is observable, so the set V coincides with T. We choose a target transition. We define a strategy. And we say that the strategy is winning if in every play that obeys to the strategy, then we can find an infinite number of occurrences of the target transition. So the player has succeeded in making this event occur forever and ever. This is a possible representation of a play which is cut from the full unfolding. So we have a part of a run, and these vertical or not fully vertical lines are the snapshots that represent the points in which we have taken this snapshot of the system. Now we have two different notions. One is the original notion of weak observable liveness with the response function defined on the transition of a net. And on the other hand, we have this idea of a game and a strategy defined on the unfolding. What is the relation between these two notions? Well, we can find a very close connection, and specifically and technically, we can, given a response function, define a strategy which is equivalent, which takes the same choices, but on the unfolding rather than on the system. And on the other hand, we can do the reverse. If we have found a strategy on the unfolding, then we can derive a response function which is equivalent to this strategy. And finally, we can show that actually the response function and the strategy are equivalent in the sense that a transition is weakly observably live with respect to a given response function if the corresponding transition in the unfolding, if the corresponding strategy on the unfolding is a winning strategy, and vice versa. So we can either solve the problem on the system by looking for a response function, or on the unfolding by looking at a strategy. And the two techniques are equivalent with respect to the final result. So, for instance, if we can find a more efficient algorithm to look for a strategy on the unfolding, then we can use that. If we have a better algorithm which finds a response function, then we will apply the algorithm, and in both cases we solve the problem of weak observable liveness. But this in the restricted case in which we can assume that the player can observe all the transitions, which is of course a strong restriction in practical applications. Quite often, if we interact with a system, we have only a partial knowledge of what happens in the system. For instance, when we ask for a service to some office, we can interact at the front office, but we don't see what happens behind the front office. So we can deduce something on the basis of our interactions, but not the full story of what happened. And so in some cases, if we look for a strategy to get the best result for us, we must rely on this partial knowledge. So we also tried to consider the case with partial observability. And in this case, the crucial notion is that of observable configuration that we already saw. So the strategy is now defined on observable configurations and chooses some of the controllable events. And also in this case, we arrive at a similar theorem. That is, we have a correspondence between the response functions in the case of partial observation and the strategy on the corresponding gain. There is a small drawback. This correspondence works only for a restricted family of response function that we have called uniform, and this is not the most general. There are cases in which one can win, for instance, in this case, one can win by using a non-uniform response function, and in that case, we are not able to derive a corresponding strategy. But still, we have a correspondence in a wide class of cases. So, we are almost at the end. Of course, so far we have reasoned in very abstract terms, finding a strategy on an infinite set. On the practical side, if we want algorithms, then we cannot work on the full unfolding, the whole infinite net. And so we are now trying for techniques that can represent the game with a finite information, but still maintaining implicitly the full information, so that we can look for algorithms computing the best strategy or the best response function in this case. For total observability, the idea that we follow is to work on a finite initial part of the unfolding, because the unfolding is infinite, but has a very regular structure. It repeats itself in some sense. So intuitively, by looking at a sufficiently long first part, we can deduce information on the whole unfolding. And for partial observability, but actually this technique we think could be applied also to the other case, we are trying to construct inductively, step by step, a strategy which will be lazy in the sense that I described on the examples. Intuitively, for the player, it is always convenient to wait for the environment to take its decisions so that we have more information and choose the best way. But of course, the player should not wait forever. So we are trying to find out when we have seen enough and we can take our decision. Essentially, these are the future developments that we expect from this line of research. So also explore restrictions to the structure of the net, working on elementary net systems with some very special properties that would allow to find more efficient algorithms, for instance. Define this general notion of lazy strategy, and also explore different notions of observability. Maybe we can assume that the player observes the local states and not the events, for instance, and this might change the nature of the problem. Finally, I want to mention that there are some other approaches to the same general idea of describing asynchronous games, namely games in which the players act concurrently and don't alternate the moves. And I have mentioned here a couple of these alternative approaches. A very interesting principle which is shared by these two approaches and we want to explore is that the idea that the player and the environment at some points interact with each other For instance, I give something to an office and expect something back. And the idea is that the players learn something, some information that could be used in the strategy only from these synchronizations. So we will not assume that the player can observe arbitrary transitions, but only transitions to which it participates in a sense. And so, well, I think this is what I wanted to present. So maybe there is some time for questions or even comments if you want.
Thank you very much.
Yes?
I have a question about practical aspects, so where to apply this approach. For instance, is it possible to apply it for computer games? Because as far as I know, finite state machines are used to formalize computer games, and there is a problem because they're really large.
Huge, yes.
Yes, so maybe Petri nets can help in this case.
I must say that I never thought about computer games, but yes, I expect that we would have a similar problem because the number of possible situations is usually very large. But it is true that at least for systems with some degree of concurrency, where things can happen concurrently, the unfolding, even if it is an infinite object, can be better than a finite state automaton, because we can stop at some point, just look at the finite initial part of the unfolding, and still deduce information about the whole unfolding. So it's not a bad idea, I think.
So there are no real computer games yet that work on this model?
No, not that I know.
No?
No.
Or at least a similar one, because this seems like, I don't know, like a very practical solution for multi-choice games. Existing games use different techniques.
Sorry, different?
Different models.
Yeah. Well, I'm not an expert in game development, I must say. So I don't know if something similar is actually used. For sure, in principle, if in a game different players can take independent moves, it's a natural formal model to represent what happens. But I'm sorry, I cannot say more because I really never looked at that kind.
What do you know about computational complexity? So the problem whether a winning strategy for player exists given some simple goal, because your definition of goal is very general.
Yes, yes. Actually, so far we have not yet really tackled the issue of complexity. I can say that in this approach, Petri games, which is quite similar because it works on unfoldings, more or less, the authors actually had to translate the problem into a problem on another kind of games, which are played on usual finite state automata. And the complexity for finding a strategy is really, even more in some cases. But for us, before being able to even trying to estimate the complexity, we should choose a specific game with very specific features, and then look for strategies. For instance, for weak observable liveness, I don't expect very efficient algorithms. But we
just by firing one specific transition, there might be hope to get some nice result, I guess.
Of course, it's the simplest.
Like the example, you just have to fire T1 and
well, the example is deceptively simple because it's really a bit constructed ad hoc to have a simple example to show in a few minutes.
so it might be an P the problem, or it might be P space hard or something.
Yes, I would expect.
Might it be undecidable?
I don't expect undecidability because we are actually working on finite state structures. So even if the unfolding is infinite, the real information is finite.
So my question is whether we can look at this study as a study of for verification of systems, so controllability maybe also.
Yeah, sure.
Correctness. So that when we develop a model before constructing a system, we can study its controllability, and then we can be sure that we can use it.
Yes, of course. For instance, the aim, the goal of the player might be to avoid the deadlock state, and so it becomes a typical control problem. We want to guide the system so that it avoids bad states or goes to a good path in the execution.
So to be reliable under some control.
Yeah.
More questions, please? So thank you very much.
Thank you for your attention.